So what I did during the spring was simulate a larger network of 16 nodes. The setting is sort of that we want to deploy a number of nodes in an ad hoc manner, and we don't really know from the beginning where all these nodes are going to be placed and how the setting looks like. And to communicate, to send information across this network, we use this DFlood forwarding protocol that will handle the forwarding of messages in the network. So that's our sort of backbone. However, DFlood alone can be quite energy consuming. So I wanted to put on an additional protocol that would calibrate the transmission power levels amongst the nodes in the network, and then on the fly, when DFlood is about to send packets, it can select suitable power levels. Yeah, so this DPower performs power calibration among pairwise power calibrations amongst the nodes in the network, and then selects a power level when transmitting. And we showed in simulations that this led to a quite dramatic reduction in energy consumption. As we can see in the top two figures, that's a network of 16 nodes without and with this DPower, the energy saving protocol. You can see that there's a sort of reduction in complexity in the network, less overhearing, less packet collisions. However, packets has to do more jumps, has to hop more times because the reach of each packet is smaller each jump. Yeah, that was what we saw during the spring. Of course, there was a little cost in that some packets will get lost as we quite drastically reduce the signal to noise ratio in this quite opportunistic method. Yeah. So what we have done during this autumn is try to get this to run in actual hardware and perform C trials to verify or show that it doesn't work in reality. So it's been a lot of visits, a lot of C trials to get everything working. There's been a lot of problems that we've had to solve over time. So yeah, as it's 16 modems are a bit too many to handle, and they are quite expensive, but we have performed the C trials with 5 modems, which we have deployed outside the Baltic Sea laboratory on Askö, and there's a fjord there called Hållsfjärden. We have deployed this many times, but in the end we have about 24 hours of continuous data collection. So these 5 modems are placed at 1 to roughly 2 kilometers internode distance, and the setting is that each of these modems are going to transmit a packet every 5 minutes, or actually 2 packets every 5 minutes, targeted at one of the other modems. And every second packet is transmitted with this power level reduction, the power conserving protocol, and every second is without, so that we have tested both with and without this power saving protocol under the same settings in the same environment, because wind and waves and so on can alter the communication quite a lot. So yeah. So each modem is moored statically in this fjord at around 3 meters below surface. We did some sound velocity measurements here to make sure that there's no strange layers where, yeah, to make sure that the modems has line of sight and can communicate. So, and yeah, here this is some results of the traffic being done in the network. In total, about 1,600 packets were transmitted with DPower and without DPower. So in total, more than 3,000 packets. Yeah, and what you can see in this graph here is lines with thickness corresponding to the high that are scaled with the number of packets transmitted over each link. I was a bit surprised. I had expected that without DPower, meaning that when all the modems are transmitting at full power, we would see a big difference between without. Yeah.
Why 2 lines?
2 lines. Yeah, it's one in each direction.
Okay.
So if, for instance, if we look at the black lines here with the DPower, if the curves bent sort of what is it, clockwise, or yeah.
The direction is clockwise.
Yeah.
If you follow the line.
Yeah, exactly. The direction of the packets are clockwise. Yeah, I had expected a little bit bigger difference between with and without DPower. It seems like even with DPower, a lot of modems are receiving most of the packets. So I had thought that some packets would require more jumps to reach the destination than they were during these settings. Maybe we should try a larger area and so on, a bit more, or force the modems to, yeah, have the greater distances and so on. But yeah, let's continue. So in terms of packet delivery ratio, we had 97% packet delivery without DPower, meaning when all the modems are transmitting at full power, and 93% with DPower. So depending on the circumstances, I would say it's a pretty small loss. Unless you really want your packets to reach the destination, then it can be pretty serious. And when we are looking at the energy consumption, each of these graphs shows the selected power level. So what you see here on the x-axis is the number of transmissions made, packets transmitted by a modem. So to the upper left, we have node number 1, 2, 3, 4, 5. And what power level was selected for each packet. And we can see that the modems generally transmitted at around -7 to -10 decibels from the maximum power, which would mean that we have used less than a 75% decrease in energy for the packets overall. Yes, so this is pretty preliminary results. I have to look further into this data because we finished up this just in the end of last week. But it looks very promising. 3-4% units of loss in packet delivery but with a 75% or more decrease in power. It's very, very promising. So what we're going to do here next is further analysis of this data. I'm going to write an article on this, and then I have some ideas for protocol improvements, maybe additional sea trials before Christmas. And then next year we are looking to do some trials with low, which would introduce also moving nodes in this network, which would make things very interesting. Thank you.